In the previous video, we learned the definition of the dot product. We saw that the dot product always gives us a scalar. We start with two vectors and the output is always a scalar. We said that the dot product can generalize to any dimension, and we have a geometric interpretation of the dot product using this formula, which more often we'll think of in this form. This formula allows us to find the angle between two vectors using the dot product. We have two very important concepts with perpendicular and parallel vectors. Vectors are perpendicular if the dot product is 0. Vectors are parallel if one is a scalar multiple of the other. Let's practice more with these concepts in some further examples. Let's take a look at example 3. Take a generic three-dimensional vector, u1, u2, u3, and we want to find the dot product of that vector with itself. If we take the dot product of that vector with itself, we have u1, u2, u3, dotted with the same thing, u1, u2, u3. To find the dot product, multiply the first two components together, u1 times u1, then the second components, u2 times u2, then the third components, u3 times u3, or we could write this as u1 squared plus u2 squared plus u3 squared. Does this look kind of familiar? What does this remind you of? Hopefully you're thinking maybe this looks something like magnitude, except with magnitude we have square root. So this expression here is actually the magnitude squared. We could write this as the magnitude of the vector u, quantity squared. In general, that will always be the case. If we find the dot product of a vector with itself, it will always give us the magnitude of the vector squared. So what is v dot v for any vector v in any dimension? Well, v dot v is always going to be the magnitude of v squared. This is an important relationship that we want to be familiar with. Take the dot product of a vector with itself, it will always be the magnitude of the vector squared. This is true for any vector in any dimension. Let's solve example 4. We want to take the dot product of these two three-dimensional vectors and see what the result is. U dot v, well, u is the vector 2, 5, 3. V is the vector -1, -2, 4. Multiply the x components together. We have 2 times -1. Multiply the y components. 5 times -2. The z components multiplied together. 3 times 4. We have -2 minus 10 plus 12. This simplifies to 0. So we have two vectors whose dot product is 0. What does that tell us? That tells us that these two vectors must be perpendicular. Just looking at the two vectors, it'd be really tricky to figure out whether or not they're perpendicular. But by simply computing the dot product, if we get 0, we can say conclusively that the vectors are perpendicular. It's hard to visualize this in two dimensions. Let's plot these vectors in GeoGebra, and we'll see that they are indeed perpendicular vectors. Here are the two vectors that we're working with. We've got the vector 2, 5, 3, which is this one here, and the vector -1, -2, 4, which is this one here. And we found that these two vectors are supposedly perpendicular. It doesn't really look like this from the view angle that we have. So if we shift our view angle around a little bit, right about there, we can really see that those two vectors form a right angle with each other. By just using the dot product, we can figure out whether or not two vectors in three-dimensional space are perpendicular to each other. These two vectors have a dot product of 0, so they must be orthogonal. Let's solve example 5. Here we're given the vector -2, 3, just a two-dimensional vector. We want to figure out which of these vectors are going to be perpendicular to -2, 3. How do we figure out if vectors are perpendicular to each other? We compute the dot product. So let's start with this first vector, 3, 2. We're going to find the dot product of this with our given vector, -2, 3. Let's see if we can do this one on our heads. 3 times -2 is -6. And then we add 2 times 3, which is +6. We have -6 plus +6. Those would cancel and we get 0. So this vector is perpendicular to the original vector -2, 3. How about the vector +2, +3? Once again, to check, we take the dot product with the original vector, -2, 3. Again, let's try to do this in our heads mentally. 2 times -2 is -4. Then we add 3 times 3. Maybe we should write out the steps for this one. Let's see, we get -4. That's 2 times -2. 3 times 3 is 9, so we add 9. And we get 5. That's not 0. So 2, 3 is not perpendicular to the original vector. Let's try 0, 4. We're going to find the dot product of that with negative 2, 3. 0 times negative 2 is 0, so we just have 4 times 3, which is 12. That's the dot product. It's not 0, so part C is not perpendicular to negative 2, 3. Lastly, how about 9, negative 6? Again, find the dot product with negative 2, 3. If we can do these mentally, it's good, but it's okay to write out the steps as well. 9 times negative 2 is negative 18, and then negative 6 times 3 is also negative 18. We have negative 36. So this vector is also not perpendicular to the original one. There's only one vector here that was perpendicular to the vector negative 2, 3, and that's this vector 3, 2. Let's use Desmos to visualize what we found here. Here's the original vector negative 2, 3. Again, to do vectors in Desmos, we just write the components of the vector as a point. Then we add a t. If t ranges from 0 to 1, we get exactly the vector that we want, just without the arrow to show the direction. But there's the vector negative 2, 3, and we found that the vector 3, 2 is perpendicular. There we go. We can see that these form a 90-degree angle, so they are perpendicular. None of the other vectors were perpendicular. So here's the vector b, 2, 3, doesn't quite form a 90-degree angle. 0, 4, nope, that's not 90 degrees. 9, negative 6, again, not perpendicular. So the only vector here that actually forms a 90-degree angle, the only orthogonal vector, is 3, 2. In example 6, we want to find the value of c such that this vector, 4, c, is orthogonal to the vector 4, 2. So some value of c here will give us a perpendicular vector to 4, 2. Before we solve this analytically, let's take a look in Desmos and see if we can get some intuition for what's going on here. First, I'm going to draw in the vector 4, 2. So there's the vector 4, 2. Now I have the vector 4, c, where c is some constant. Desmos allows me to add this slider for c. As I move the value of c around, I get these different looking vectors. And I want to know which one of these is perpendicular to the original vector 4, 2. Well, it looks like if I go any higher, if the y value goes higher, I'm not going to ever get a perpendicular vector. So how about lower down? Oh, look at the angle. It's looking closer and closer to 90 degrees. Right about there, looks like we have a 90-degree angle. So I'm going to guess that if c equals negative 8, I'll get a 90-degree angle. Let's confirm that algebraically. Now that we've got a good guess from Desmos what the answer should be here, let's find that analytically. We want to figure out what is the value of c so that this vector is perpendicular to the vector 4, 2. So here's what we want. We want to compute the dot product of 4, c with 4, 2, and we want this to equal 0. Let's just compute the dot product here on the left-hand side. 4 times 4 is 16, plus c times 2, that's just 2c. We want this to equal 0. So we're going to solve for c to figure out which values work. We have 2c equals negative 16, divide both sides by 2. c equals negative 8. That's exactly what we found from Desmos. The correct value for c here is negative 8. If we use that for c, we get two perpendicular vectors. Let's solve examples 7 and 8. We are going to use the geometric formula for the cross product to find angles between these given vectors. First, we'll work through problem 7. Let's write out the problem here. We want to find the angle between, we've got the vector 3i minus 2j plus 6k, and also the vector 6i minus 4j plus 12k. I personally don't enjoy working with vectors in the ijk notation. I like to use the component form, so I'm going to convert these. I have 3, negative 2 for the y, and 6 for the z. The second vector is 6, negative 4, 12. We're going to use the geometric formula for the cross product to calculate the angle between these. Specifically, here's the formula that we'll use. Cosine of the angle between the two vectors is the dot product, u dot v, divided by the magnitudes of the two vectors. So let's just call this first one u, and then the second one will be v, and let's compute this expression here. We'll go ahead and find the magnitudes first because we need those in the formula. The magnitude of u is the square root of 3 squared, which is 9, plus 2 squared, plus 6 squared. If we simplify this, we have the square root of 49, which is 7. So that's the magnitude of u. Let's find the magnitude of v. We have the square root of 36 plus 4 squared is 16. 12 squared is 144. These numbers simplify to 196. Square root of 196 is 14. That's the magnitude of this vector v. Let's plug those into the formula that we've got here. We have u dot v in the numerator, and we'll divide by 7 times 14. Let's calculate the dot product now. 3 times 6 is 18, plus negative 2 times negative 4, that is plus 8, plus 6 times 12, that's plus 72. Working through this arithmetic, we are going to get 98 in the numerator and also 98 in the denominator, and this simplifies to 1. So we have cosine of the angle between the two vectors equals 1. We want to figure out what is theta. What is the value of an angle so that the cosine equals 1? Let's draw the unit circle here to help us think through this. Cosine is the x value. Where do we have an x value of 1? We have that right here. That's at an angle of 0. So theta here is 0 degrees. What does this mean? If the angle is 0, this means that the vectors are parallel. Well, hang on a minute. Could we have figured that out without going through all this work here? I think we could. Take a look at the two vectors that we originally had. If we multiply this first vector by 2, we'll scale it up, and we'll get the vector 6, negative 4, 12. These vectors are just scalar multiples of each other, so of course they must be parallel. But we verified that using the geometric formula for cosine. Let's work through an example where the angle between the two vectors is not 0. This will be example 8. We want to find the angle between these two three-dimensional vectors using that geometric formula. For example 8, we want to find the angle between the two vectors. Well, the first one we'll call u. This is the vector 3, 3, 0. The second one we'll call v, which is the vector 4, 0, negative 4. Once again, we are going to use the formula cosine of the angle between the two vectors is equal to the dot product divided by the product of the magnitudes. So we'll again focus on finding magnitudes here, and then find the dot product to get the answer. Magnitude of u is the square root of 3 squared plus 3 squared. 3 squared plus 3 squared, that's 9 plus 9. We have the square root of 18. Magnitude of v is the square root of 4 squared plus 4 squared. 16 plus 16. We have the square root of 32. There's our magnitudes. Now let's compute the dot product to get the numerator here. We have the dot product. 3 times 4, that would be 12. And then 3 times 0 is 0. And 0 times negative 4 is also 0. So the second two terms here in the dot product are just going to be zeros, because when we multiply the two middle components, we have 0. When we multiply the z components, we also have 0. So the dot product here is just 3 times 4. 3 times 4 divided by magnitude of u times the magnitude of v. Here's our expression for the cosine of the angle between the two vectors. If you plug this in a calculator, or work through the steps by hand, you will get an answer of 1/2. This whole fraction just simplifies to 1/2. So we have cosine of the angle between the two vectors equals 1/2. What angle gives us a cosine of 1/2? Let's think of the unit circle again. Cosine of 1/2, well, that's an x value of 1/2. That's right about there. So the angle that we need is right about here. This angle is pi over 3 radians, or 60 degrees. So we could say here that the angle between these two vectors is 60 degrees. We found that using this geometric formula that involves the dot product of the vectors. Let's go ahead and visualize this in GeoGebra. Here are the two vectors, 3, 3, 0 and 4, 0, negative 4. Based on this view angle, it does not look like they have an angle of 60 degrees. They look parallel. So if we move around a little bit, then we'll really see the angle between the two vectors. So right about there, that looks like about an angle of 60 degrees. Using the dot product, we found that the angle formed between these two vectors is 60 degrees. This is true for any vector.
This is true for any vector. Why are you calling them vectors? Vectors.